Well, we've literally all been there, right? You walk into a store or maybe you log onto a website trying to snatch up those concert tickets, and suddenly, boom, you hit a wall, a line, a queue. We sigh, we compulsively check our watches, and we just endure that universal, deeply relatable frustration of waiting. But what if I told you that to a mathematician, that highly frustrating line is actually kind of a beautiful, intricate puzzle? Welcome to This Explainer. Today, we're going completely behind the scenes into the source material on queuing models. See, this isn't just about standing in line, it's about the rigorous academic and mathematical frameworks that engineers, computer scientists, and business managers use to analyze, manage, and ultimately solve the problem of waiting. We're going to decode the invisible architecture running your everyday life.
Okay, let's dive right into this. We're going to construct our understanding of queuing models block by block. Here's the roadmap. First, we'll look at queuing systems and structures. Second, single versus multi-server models. Third, input and service rates. And finally, finite and infinite populations. Part 1, Queuing Systems and Structures. The foundation of flow.
So to really grasp the science of waiting, we first need to define our base framework. A queuing system is the overarching mathematical structure used to analyze, manage, and optimize waiting lines. Think of it like a master blueprint. When academics toss around this terminology, they aren't just talking about a physical line of people shuffling forward. No, they're talking about a highly structured system of flow. This could be a totally generic grocery store managing carts at the front, or it could be a digital server processing literally thousands of data requests per second. The math, surprisingly enough, remains exactly the same.
Now, to analyze that overarching framework, we've got to break it down into its core components. Every single queuing structure, no matter how wild or complex, fundamentally relies on these three pieces. First, you have the incoming arrivals, who or what is actually entering the system. Second, the waiting line itself, basically the holding pen where entities just kind of exist before being processed. And third, the service mechanism, the point where the actual work gets done. By isolating these three specific variables, modelers can manipulate the whole system. Throughout this explainer, these are the exact puzzle pieces we'll be tweaking and tuning to see how the flow changes.
Moving right along to part 2, the checkouts, single versus multi-server models. We just mentioned the service mechanism, right? Well, in queuing theory, the structural arrangement of those resources is known as the server model. A server is simply the mechanism providing the service. It could be your favorite barista, a toll booth operator, or a high-powered computer processor. The absolutely vital thing to understand here is that the way you arrange these servers, whether physically or digitally, dictates the efficiency of the entire operation. It sets up a totally crucial structural comparison that modelers have to make right out of the gate.
Now, what's really interesting about this is the vivid contrast between these two structural flows. Take the single server model. It's as simple as it gets, really, one line feeding into one dedicated service point. But then look at the multi-server model. Here, we've got a queue feeding into multiple parallel service points. Think about how altering this one seemingly small structural element changes the entire dynamic. Adding multiple servers doesn't just process people a little bit faster, it fundamentally changes the mathematical probability of a bottleneck. I mean, if the single server gets stuck on a difficult task, the whole system just grinds to a halt. But in a multi-server model, the flow simply diverts right around the blockage to the next parallel point. It's brilliant.
All right, part 3, the flow, input and service rates. If you spend any time digging into the source material on queuing models, you'll inevitably run into the term Poisson input. I know, it sounds incredibly dense and academic, but it's actually describing something highly relatable. A Poisson input is just a mathematical model representing arrivals that happen randomly and independently over time. Picture customers walking through the front door of a local coffee shop. The shop might average, say, 30 customers an hour, but they absolutely don't walk in neatly spaced exactly 2 minutes apart, right? 3 might walk in together, then literally no one for 10 minutes, and then a sudden steady stream. The Poisson model captures this everyday, unpredictable reality, allowing mathematicians to actually plan for the chaotic nature of human behavior. This matrix right here highlights the absolute tension at the heart of queuing theory. It elegantly illustrates the relationship between our unpredictable Poisson input and two vastly different processing types, exponential service and constant rate service. On one side, you have the pure, unadulterated chaos of random arrivals. And on the other side, you have the mechanism desperately trying to process that chaos. The relationship between these unpredictable inputs and the rate at which they're handled, that's what will completely determine whether your line moves smoothly or backs up out the door. Let's look a little closer at these two processing types. First up, we have constant rate service. Notice the completely equal, perfectly uniform bars. This represents a system where every single transaction takes the exact same amount of time every single time. Zero variance. Think of an automated car wash. Once your car is on that track, it takes exactly 3 minutes, whether it's a tiny compact car or a massive SUV. When your service rate is a constant, mathematically uniform flat line like this, it becomes incredibly easy to predict and manage the queue, even when your arrivals are completely random. But contrast that with exponential service. Characterized by those wildly varying, rapidly decaying bars, this processing model is a totally different beast. In exponential service, processing times vary wildly from one entity to the absolute next. Think of a human customer service desk. One person walks up, maybe they just need a quick signature, boom, 10 seconds, they're done. The next person, they might have a massively complex issue requiring 15 minutes to unravel. When you combine random pass-on arrivals with wildly varying exponential service times, you get a highly volatile dynamic for the waiting line. This, my friends, is the exact recipe for those sudden, massive traffic jams we all hate.
Which brings us to part 4, the crowd. Finite and infinite populations.
So, the final crucial building block is understanding the scale of who can actually enter your system in the first place. Here we contrast a finite population with an infinite population. A finite population is a closed system with a limited, set number of potential users. Take an internal IT desk that only serves a company of exactly 50 employees. The math literally caps at 50. Contrast that with an infinite population, an open system with a theoretically limitless number of users, like a major public retail website. Building a model for a restricted, closed pool of people differs entirely from planning for an endless, infinite flow. Think about it. If 5 people are in line at that IT desk, there are only 45 left in the entire world who could possibly show up. If 5 people are on a retail website, millions more could still log on at any fraction of a second.
So let's pull back and see how this all builds together. We've taken apart the source material to reveal the 4 vital steps engineers take. 1, they define the basic system structure and its components. 2, they choose the server layout, single or multi. 3, they determine the mathematics of the flow, contrasting random inputs with constant or exponential service rates. And 4, they account for the population size, finite or infinite. By stacking these independent source variables together perfectly, we build comprehensive, highly accurate queuing models. It is just a brilliant way to quantify and control the chaos of reality.
And just like that, we've reached the end of our structural breakdown. We've taken the abstract terminology of queuing theory and shown exactly how these mathematical frameworks dictate the flow of the modern world. You now know about Poisson inputs, multi-server arrays, and exponential service times. You know the exact variables that dictate whether you breathe through a checkout or stand there utterly frustrated. So I want to leave you with this final thought. Next time you find yourself standing in a line, compulsively looking at your watch, take a moment to look around. Ask yourself, is this a single or multi-server model? Are the processing times constant or are they exponential? Next time you wait, what invisible mathematical model is controlling your time?